Well, the journey started in Barcelona in Spain. I was doing a PhD in aeronautical engineering or aerospace engineering. And I was working on a PhD project to make a device that would go to the moon, take the lunar regolith, which is the moon soil. It's predominantly silicon and oxygen, and convert it into solar cells and breathable oxygen. There's one real critical part to do that, which was a carbon nanotube. I'd never heard about this before. And the idea at the time was that we would either buy the nanotubes or we would make the nanotubes ourselves. At that time, it was incredibly expensive, so I had no budget. So we decided we'd learn to make them, and it was a kind of a dark art. This is 15 years ago. By a very circuitous route, the International Space University were doing a summer program on nano engineering applications in space. So I got into that. I did that program. And in applying for funding for that, because it's pretty costly, I had made lots of emails to lots of different people. And someone in the Irish government reached out to me and said, we don't have funding for this particular program, but if you are interested in nanotechnology, we do have a different program where you go to America and do nanoengineering. So I said, show me the details. And it was to go to Rice University, which is one of the eminent universities in the US, especially for engineering and for nanotechnology, to do a project on growing carbon nanotubes. And it was the only project that was still available in the program. So it was kind of like, the satellites and the stars aligned. My advisor, my PhD advisor at the time, said to me, the best thing that can happen to you is you don't come back. You go to America, you learn this from the best people, and you just go onwards from there. So he gave me his blessings and his support, and so I went to Rice University, and that's where I began to learn to make carbon nanotubes for myself. I got really taken by the idea of changing the electricity grid network through being inspired by the late Rick Smalley. He'd won the Nobel Prize for discovering the Buckminster fullerene, which is a sister molecule to the carbon nanotube. So working amongst people who are Nobel Prize winners was really inspiring, because oftentimes you forget it, but really when you look at these Nobel Prize winners, they're working on things that other people give up on and don't do. And that's sometimes just what they get the Nobel Prize for doing, is something that other people just didn't want to do or haven't thought about. And they do it in new ways, and they have that boldness of spirit to do it. There was one project left open, which was to grow carbon nanotubes, and it was to grow carbon nanotubes under the supervision of Professor Andrew Barron. I'd read about him and I'd read about his work, which was still new to me because I didn't know about carbon nanotubes. But one of the interesting things was, when I did my homework on him, I saw a video recording from Discovery Channel. That was it. He did a video on Discovery Channel. And the way he introduced himself, he was in his race suit with his race helmet, and he goes, I'm Professor Andrew Barron, a race car driver and a professor in chemistry. And I was like, this guy's pretty cool. And when I was working with him, I was like, Andy, I have other hobbies and other things that keep me engaged. Like, I'm a DJ, and on some weekends there was a time when I was actually more actively involved in that. I was doing a small, once a month kind of nightclub. And he was like, yeah, I do that. Like, when I was in my PhD, I was doing the lights for Pink Floyd. You do what you have to do, and then so as long as when you come to work, you come to work. And I was like, okay, yeah, I can get with this guy. This is fine. So he's really a powerhouse, and also been a very big influence and an inspiration. Again, I go back to that aspect that I said, where you find that one way it can work, you focus on finding that one way it can work, and then you find suddenly there's actually 10 ways, and then suddenly there's 100 ways. He embodies that all the time. You go after these big challenges because they're needed. You need to go after these challenges. You can't let them by just because you go after easy things. You have to go after challenges that are meaningful, not just for yourself, but for others. So I had a very intense uptick in my, I had to go from a background of physics to doing chemistry, learning chemistry. I went first as an intern, and then I got accepted into the PhD program and stayed as a PhD student. And it was really very inspiring to work with people who were looking at a really intangible, tricky, challenging, virtually impossible task. The thinking is very simple. From looking at the videos of Rick Smalley and reading his texts, what he was saying was, if we are going to survive as a species, what are the biggest challenges that we have to overcome? So he had access to lots of different people to ask this question. And over time, he synthesized it down to the top 10 challenges, the grand challenges, or the top 10 problems. And on the top, he put energy, because it always turned up to be in one of the top 3. But he realized you have to solve the energy problem in order to solve everything else. If you want clean water, you want sanitation, you want to prevent disease, you want prevent crop failure, poverty, you need energy to do all of this. And it was really a critical aspect. So energy is down to generation, transmission, and storage. At the time, we were, and even now, we're using the same amount of power roughly than 10 years ago. Actually, we're using more now because of what, society continues to grow, more people are getting electricity. And now with the advent of artificial intelligence and so on, there's going to be even more requirement for electricity and energy demand. But people need energy to survive. It's not just a matter of good living standards. People need it to live. When we have energy failures, people die. And if you look at the amount of energy we get from the sun, it's in one day we get the same energy from the sun that we use on the planet in an entire year. So generation shouldn't be a problem. So what is the problem? It's actually the fact that where the sun shines, people don't live. Where the energy is created, people don't live. Or where the source of the energy is, people don't live. People don't live in the North Sea, where you get the oil from. People don't live in the desert, where you get all the sunshine. So you have to transmit it. And that now what we do is we transmit it as a mass, as a material. We ship it as coal, we ship it as oil. And that takes a huge amount of energy just to do that. That's embedded. So why don't we ship it as electricity, generate electricity? And that's because the conventional cables don't work to what we need them to. They lose electricity over distance, even short distances. They lose electricity. So that's why power stations have to be beside the populations. You can't have power stations out in the countryside and then have the material brought in. That's why you always have power stations close to where the people need the electricity. So that was one issue that he looked at, is the transmission issue. So you see the immediate problem. It's down to the fact that you have inherent, intrinsic problems with metal wires. What could you use instead? Look around the board, and carbon nanotubes is a material that has far greater current carrying capacity, 1,000 times greater current carrying capacity than metals, far lighter, much lighter weight, at least 6 times lighter than copper, and it also transmits heat. So if things heat up too much, it can transmit and dissipate that heat, so you don't get hot spots. So it was an immediate material of interest for him. And so he dedicated pretty much the rest of his life, because he had a short life, he dedicated the rest of his life to that goal. And again, all these other professors who I was working with in the Smalley Institute were also very dedicated, and some of them still are entirely dedicated to seeing this goal through. And then you come into the third aspect, which is storage. And this is where we're at now. We're in a new era now of storage. You see a lot of talk about electric vehicles, but it's not just electric vehicles that need batteries. A lot of other houses are going to need batteries. You're going to need more batteries in industry. There's there's articles just come out in the Financial Times where there's companies that are focusing on those types of batteries, because they're really the batteries that are going to make the biggest shift in terms of energy storage. And carbon nanotubes are a common material in batteries already today, and they're also part of the future of batteries. So carbon nanotubes have now found itself both in the aspect of transmission, but also in the aspect of storage. And so my journey has been my journey has really been focused on seeing this vision through. I'd like to leave the planet in a place that's better than when I arrived. Especially now I have children. It's such a classic thing. You say, oh, you have children, and suddenly you change your perspective. I had that perspective before, but it certainly gives much sharper focus on the meaning of that. One of the key challenges with carbon nanotubes was to make them at scale at an affordable rate. It always starts with like, okay, well, we can get copper. We know how much it costs to make copper wiring. Can you compete with copper wiring? And so that's one of the big issues, was to make things at cost. Another issue was, Well, the stuff we were making in the lab was fantastic, very, very clean, very, very long, or have like excellent properties. But to make that at large scale so that you could replace or augment all the metal wiring is a challenge into itself. And then also when you think about a commerce perspective, especially in terms of manufacturing, you can't have inconsistency. Like when you go to get a pint of milk, you know you're getting a pint of milk. You're not getting yogurt one day and kefir another day. You're getting a pint of milk. And manufacturing requires that consistency. So these are the three problems. So some research group in Rice University realized that actually one of the shortcuts to achieving this wire technology would be to make nanotubes extremely long, what we call ultra long. And it's a simple philosophy really, because it's like if you have a hemp material, a hemp rope, the hemp fiber, the length, the size of the individual hemp fiber makes a difference in the strength of the rope. So having longer individual fibers of individual components makes a difference in the conductivity of the wire thereafter, because you have less junctions, less junction resistance. So by sheer luck, I went to MIT. Well, the luck really was that at MIT, when I arrived, my job was to help the research group there grow their nanotubes, and there were lots of people in that research group who were growing nanotubes, and they needed a chemist to come in and help them with that process. But also I got to be part of writing a grant proposal for making ultra-long carbon nanotubes. And we'd heard about these carbon nanotubes in the community, and in the Smalley Institute we were talking about them, and there was one group who was there who tried for 2 years to make them to no avail, to no success. So I kind of thought maybe it was not possible, because you have to understand a nanotube is a molecule. It's a tiny little molecule that's 70,000 times thinner than your human hair. It's about the size of your DNA, right? It's incredibly small. Consider it in molecular terms. But an ultra long carbon nanotube is so long, it's centimeters in length. That's a material. So at a certain stage, it goes from being a molecule to a material. So the dynamics of how you make it and process it and think about it changes. So we kind of thought maybe it wasn't possible to make ultra-long carbon nanotubes if this esteemed group weren't able to make it after a 2-year time frame. Then I was at MIT. I got to write a project or write a grant to be part of that grant, and then I did make my own ultra-long carbon nanotubes, single walls. And then I was like, right, it's not a concept. These papers that are coming out are true. This is possible. And the way I like to think about it is when I did my PhD in chemistry, I thought about atoms and molecules, catalysis, thinking about things at the small fundamental level. When I went to MIT, I was in the Department of Mechanical Engineering, and so you kind of take a step back, respecting that you still need catalysis to work, but you also start thinking about the machinery in which the catalysis is occurring. And so I started to think about, okay, well, how do we change the reaction dynamics and think more about the physics of the process? And that's where, because again, I said, you go from the molecule to the material. The molecular thinking needs catalysis and chemistry, but the material thinking needs more mechanical engineering and physics. So you have to have all these other aspects in the thought process. And then, as would happen, my journey continued, and I became eventually an associate professor in chemical engineering. So I came into chemical engineering, and I could see, again, I started out with a degree in physics. I can understand how you can apply, the laws of science to chemical engineering. But what I took from it then in my journey was, now in chemical engineering, you think about a whole series of devices. So again, starting out with the molecular interactions in chemistry, thinking about how you make the devices so that these can occur in terms of mechanical engineering. And then in chemical engineering, you think about, well, how could you make multiple of these together so that you have a system? Because that's what chemical engineering is. It's a system. You have an input, and then you have a final product and an output. You look at the economies of scale, and often you talk about scaling things up in chemical engineering. And that's my journey. It was quite interesting. Looking backwards, you can see the lines between the dots. But looking forward, it was really just, you get the best opportunity you can, and you make the best of it that you can. And then you guided by a vision, you keep moving towards that vision, and you find ways that, you envelop your skill set into solving that vision. I'd always been thinking in the back of my mind, and if we're going to make carbon nanotubes to replace the metal grid wire, it's probably, it's 13 million miles of cables in the US alone. It's probably going to take, back of the envelope calculation, maybe 100 million barrels of oil just to have that carbon, if it's a one-to-one swap in terms of the size, same volume. So where are we going to get that carbon from? Are we going to go and get virgin oil, or are we going to find the carbon from somewhere else? So that's when I started to investigate other sources of carbon. The Welsh government were really keen to increase the level of science output and engineering output from their universities. And they put together a long-term plan. They hired multiple people from around the world to come to Wales. And one of them was Professor Barron, and they gave him, a large packet of support. And I wrote a fellowship to come to Swansea, and I spoke with Professor Barron, and he was the chair of chair of low carbon technologies at the Energy Safety Research Institute, which he had set up himself. And he thinks about safety, energy safety, from the perspective of safety of supply, security of supply, that we don't end up in a dark world with no electricity and madness, chaos. Where do we get our electricity from? Where does the power come from? And how do we utilize it best? So he had a number of different aspects of that he set up, and one of them was power distribution and materials for that. So he put a great offer on the table with excellent instrumentation and device and support. And then I looked at Wales from the perspective on the outside, and I thought, it's a very progressive nation in the way that it has great laws for and habits for recycling. So I thought this could be a good place to look at non-traditional sources of carbon, because they already have this context of having a clean environment. And I found out later it's written into the Future Generations Act about having more sustainable living. And so I thought, again, the stars aligned, and we came here over 7 years ago, and I started out my research looking into non-traditional sources of carbon as a form of carbon for making these ultra long, or making these carbon nanotube wires and cables. One person in my network was like, Alvin, I'm chairing a meeting in Westminster on Tuesday, you should come. Of course. And then Andy was like, well, if you're going to Westminster, you better patent that technology. So we filed a provisional patent and moved from there. And yeah, I went to Westminster and had that, pictures of that graphic and different demonstrations that I could have at hand, and spoke with people and started making the network and letting people know that this was a possibility. And it kind of, I get similar questions all the time. Some people are like, really? It takes a while, because they think of plastic as, when you think of plastic recycling, probably the first thing you think about is it just stays plastic. Isn't it? It's like plastic in becomes plastic out. It's just a different form of plastic that's inferior to the original plastic. But I'm like, no, this is not plastic recycling. This is chemistry. It's chemical conversion. I'm taking the carbon atoms from the plastic and making them into carbon atoms in a nanotube. It's a completely new material. It's like, sorry, wait, can you start that again? And it's like, there is carbon in the plastic, and through a process of chemical vapor deposition and catalysis, or through a simple catalytic process, or basically it's just like Lego. You just jumble the Lego blocks and then put all the yellow ones together, and that's now a nanotube, and all the blue ones, that's all the hydrogen. And that's really what we do. We think about it from that perspective of just, you take the carbon atoms, you reassemble it to make the carbon material that you need, and hydrogen. And so that's when the journey began. And there wasn't even a company at the time. That's eventually I formed TrimTabs to commercialize the technology and to bring it forward, because I thought this needs to see the light of day